We are going to wrap up section 1.4 with some examples about looking for where some logs, some trig functions are continuous. So in the last section when we defined continuity, we said that certainly one culprit is always where a denominator goes to 0. So as I look at this first example that I've already written down, so we already would say to ourselves, well, I definitely know that x minus 5 is equal to 0, of course, when x is equal to 5. So I know I'm going to have, let's say, a discontinuity, or it's going to be discontinuous whenever your denominator is going to go to 0. So we always know that. Okay? So we certainly have a discontinuity, a place to throw out a value at 5. Now, the other situations, we have kind of two issues to concern ourselves with here. So that was our first one, was looking at any place that would make our denominator go to 0, and that's at x equals 5. Okay, so that's one issue to concern ourselves with. Now, the other issue, and I mentioned this, I think, briefly in an example involving a limit of a log function. But logs, if you recall, kind of like square root functions, not exactly, but logs have to be strictly positive. Square roots, even index radicals, can be positive or 0, greater than or equal to 0. Logs have to be strictly positive. So when we're looking at this issue right here, we need to know that anything inside of a log function must stay greater than or strictly greater than 0. So log functions have to be positive. All right, well, if we solve this for x, this is going to involve, of course, adding 1. And then we can divide by 2. And remember, if you are ever dividing by or multiplying by a negative with inequalities, you do need to reverse your inequality. We're not here, so we need to reverse that inequality. So we have sort of two issues here as we sort of pull this together. And maybe I will rephrase my language up here, although it's true. So it's a discontinuity where the denominator went to 0. So let's just say where it is continuous means I'm going to have to throw out the value here where x, where the denominator can't equal 0. So if I'm trying to state where something is continuous, this probably looks a little bit better. So I'm trying to state where something is continuous. So if it is continuous, it's where the denominator can't be 0. And where it is continuous is where the log functions are defined, which are logs of positives. All right, so together, when we pull that information together, let's look at what we have here. So the log is positive when I have x greater than a half, but I also have to throw out where x is equal to 5. So together, when we bring both of these pieces together, okay, we are going to end up with, so pulling these together, where the function is continuous is going to start at 1/2 with an open parenthesis, strictly greater than, to 5 parenthesis, to throw out the 5 union or comma, picking up at 5 and then going to infinity. So this is where f would be continuous. So kind of bringing in a concept from before that you've known for a long time, denominators can't be 0, and we also talked about in the last section. And then just also recalling from your good old college algebra pre-calc that logs have to be positive. All right, so other situations that you might be encountering here. Okay, let's look at another example. And again, we are looking to identify where the function is continuous. So suppose I have f of x is equal to, and let's just talk about, I'm going to change the question I had written out. Let's say we have 3 tangents of 2x. So what I want you to remember is, in general, when you're talking about trig functions, sine and cosine, those are continuous everywhere. But when you get into tangent, cotangent, secant, and cosecant, those are functions that really do have hidden denominators. We have to rewrite them as their quotients or their maybe reciprocals, but they do have denominators. And once again, just kind of like up above, we know that we have to avoid where the denominator is equal to 0. So we know that cosine of 2x is not going to be able to be 0. A denominator can't be 0. So we have to figure out all the x values that would make cosine 0. So let's kind of think about that here. So let's just kind of go off to the side here, and let's first think about, so I'm trying to find, so let's find where cosine of 2x is equal to 0, and then of course we will, throw those values out of our continuous intervals. Well, I don't know, cosine of 2x, that's a little trickier. So often what you might say, you might have done this, I hope, in like a trig course, is let's start with something that's a little bit easier. Let's think about where just cosine of theta is equal to 0. So for what theta is cosine 0? Well, when you think about your unit circle, where cosine, or your x-coordinate, and your unit circle is equal to 0 is at pi over 2 and 3 pi over 2. Those are your two values that are on the fundamental period from 0 to 2 pi. But this function did not give you a restricted domain. So you got to think about all of them. So you could keep adding increments of pi over 2. So plus 3 pi over 2, and then that would take you back around from the interval to 0 to 2 pi, all right? And then if I go all the way around from 0 to 2 pi and I add another pi over 2, so basically one full rotation of 2 pi and then plus back up at pi over 2, so 2 pi plus pi over 2, that's going to put us at 5 pi over 2. Okay, and so what am I really doing in between each of these? I'm adding on increments of pi. So every time we're adding another pi, which is another 2 pi over 2. So we end up with, 7 pi over 2 and so on. But you could also go in the other direction. You could have negative rotation. So you could have these same values, but going in the other direction. And these are going to continue forever and ever in both directions here. All right, now we can come up with a better representation for that, and we will. However, theta was just a temporary fix. Theta was really equal to 2x. So theta is really 2x. So these are all really kind of like a bunch of different equations where 2x is equal to each of these, pi over 2 and so on. So this is really 2x equals each of those. So now if I need to solve for x, I am just going to divide all of these equations, basically. I need to divide them. I did not mean to erase that. Darn it. So that was my 2x. All right, so now I would divide by 2. So I'm isolating for x. So I'm going to divide both sides, so all of those values, because it's like having a bunch of little mini equations. We divide them all by 2. So the values then for x, which is really my original variable here, Dividing those all by 2, we end up with negative 3 pi over 4, negative pi over 4, pi over 4, 3 pi over 4, 5 pi over 4, and so on. So we end up with these being our kind of infinite set of values that, again, remember, these are the values that we have to throw these values out. So that means that the function is continuous. I'm going to choose to kind of write this one with some set builder notation. So the function is continuous everywhere except for these values. So there's a couple of ways you could write this. So you could say the set of all x such that x is not equal to, and so if we look at kind of what we have here, what's kind of happening, we're at pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4. So every time we're still adding or subtracting an increment of, in this case now, we're adding and subtracting an increment of pi over 2 in between each of these, right? So if you added pi over 2 in between any of these, that's the same thing as 2 pi over 4. So if you added, 2 pi over 4 in between any of these, or pi over 2, you're going to get the set of all values. So here's a couple of different ways that you could write this out. You could say it is the set of all x such that x is not equal to, and you could start with maybe just like the first value, and you could say pi over 4, and then you could say plus any increments, and we said we were adding increments, integer increments of pi over 2. We could just say where n is any integer. So that's kind of awkward, I think. As a matter of fact, I had to kind of force myself to write it out that way. I'm not real keen on that. But this is one way that I, would accept, and it's a starting point. It takes the first value and just figures out what am I adding or subtracting to those values every time. Now, if you think about actually getting a common denominator to this, again, if this is n pi over 2 and you multiply by 2 over 2, this would become 2n pi over 4. So now I have pi over 4 plus 2n pi over 4. If I add those up, I get 1 plus 2n pi plus 2n pi all over 4. And if I factor out the pi, I get 2n plus 1. So this is a long, convoluted way of saying something that I just kind of want you to observe. Odd numbers actually get represented by a sequence of numbers in the form of 2n plus 1. Even numbers come from a sequence of values of 2n, where n is any integer. Odds come from a sequence of 2n plus 1, where n is any integer. So if this is all a bit much for you, don't panic. It's okay. But I'm just trying to expose you to, a couple of different ways to denote this. So the other way, and what was sort of my initial instinct here, but it probably would not have been for a lot of students, would be to say the function is continuous everywhere except for, so the set of all x such that x is not equal to 2n plus 1 pi over 4, where, again, n is any integer. So there's a lot to unpack in that example. First and foremost, we had to throw out values that made a denominator 0. Second, we had to think about where is cosine of 2x equal to 0. Well, that happens where cosine of theta goes to 0. And then we replace theta with 2x and kind of divide everything through by 2. I would say if you were able to follow along with those first, few lines of work, you're doing good. You get down to then kind of the final answer. Either of these representations would be absolutely fine. And there would be others. I think that your book kind of goes with one of those types of representations. All right, so let's look at just one last example here. So suppose I have a little piecewise function. Last one here, f of x equals, and let's do tan inverse of x, or arctan if you prefer, if x is less than 1, and natural log of x if x is greater than or equal to 1. All right, so first of all, kind of just note, we know that logs are only defined for positive values, but the natural log function in this piecewise function is only for values of x greater than or equal to 1, so we're good there. Arctan, if you remember, just as a little recall off to the side here, your arctan of x looks something like this. Has horizontal asymptotes at pi over 2 and negative pi over 2. So its domain is all real numbers. There's no restricted domains on arctan. So we're talking about tan inverse there. So neither of these right now are causing me to think I'm going to have any restrictions. The only thing I need to then do is investigate, like we did in the last section. I am going to have to investigate continuity at that cutoff point. So I need to investigate what's happening with my continuity at this cutoff point of x equals 1. And this is where we do it with our 3-part definition. So step number 1, we need to look to see, is this point even defined? So we want to start and just look at what is f of 1. So here we're looking for where it's defined, so where it's equal to. And so we're going to sub in to our natural log of 1, and natural log of 1 is 0. It passes. Step number 2 is looking at our limit as x approaches 1. Now, because we have a cutoff point of a piecewise function, this is where we have to know to look at the limit from both sides. So the limit as x approaches 1 from the left, that means we're coming in from values less than 1. So this is going to be our tan inverse of 1. And so this, you should be thinking about essentially, for what value of tangent is tangent of theta equal to 1. And so that is going to be pi over 4. All right, now I have to look at my limit from the right. So the limit as x approaches 1 from the right of f of x, well, that is, again, right of 1 is coming in from values bigger than 1. So this is natural log of 1, but that is equal to 0. So in this situation, because the left limit is not equal to the right limit, that tells us that our overall limit does not exist. So the limit as x approaches 1 of f of x does not exist. So we fail here at step 2. So we're not continuous at x equals 1. This question is about where is the function continuous. So our final answer here would be stating the opposite. So f is continuous from negative infinity to 1, open parenthesis, union or comma, 1 to infinity. And so that would be our final answer. All right, so that's it for this section. And when we come back next time, we're going to look at some limits involving infinity and also some asymptotes. So that's what we'll be starting in 1.5 next time.